Hey everybody. In this video, we'll talk about how to measure and what to measure. First of all, how do we set up a display for measurement? We need to remember that a display and the computer driving it behave together as a system, and there are many variables in that system that must be controlled for robust measurement. The state of that system at measurement will be the state of the system preserved in the characterization model. Before we do anything, we must turn off automatic things like screensavers, power savers, automatic brightness adjustments, automatic color adjustments such as night shift or F-lux or true tone. Next, consider warm-up time. It takes 30 to 120 minutes for a display to warm up and stabilize. Remember this when you use it for an experiment. The same warm-up period will be required at the start of each day. Also, you may have noticed the displays, especially LCDs, have an angular dependence. They look different, generally worse, from oblique angles. Because of angular dependence and possibly spatial non-uniformity, the best choice is to measure the display from the perspective of the viewer. What that means in practice is to set up the display on the desktop, in the lab, or wherever, angled as needed, and then the measurement device is placed where the viewer would be. Pictured in this diagram is a spectroradiometer, which takes a measurement from a distance through a lens, much like a camera focuses on a distant object. This is different from a calibration puck that measures while in contact with the screen. Those work okay, but they don't sample the light output in the same way that the viewer's eyes would, and so there's a potential for error. I would typically use a spectroradiometer arranged like this, aimed at the center of the display and pointed perpendicular to the display surface. If an experiment would use different regions of the display, then maybe other regions should be measured as well, first to confirm that they behave the same, and if not, to build compensated display models for different regions of the display. Other details to consider are operating system settings, color management settings, program-specific settings. For example, if our experiment will use MATLAB, it would be best to measure using MATLAB to generate the color samples. This is also handy because with a programming language like MATLAB, it is easy to set up a measurement loop to do a long sequence of measurements. The measurement program would look something like this. You load n RGB code values, and you loop over I n times. In each loop, set the screen color I, set the screen to color I, then measure it. Keep doing this until all the colors have been measured, and then build the model. So the next part is to figure out what to measure. Remember that characterization means building the model and verifying it fits well. That implies that we actually have two sets of data, measurements to build the model and measurements to verify the model. They're independent. Actually, before we can build the model, we should test the assumptions. Remember, channel independence, constant chromaticity, and constant black offset. I'll leave those details out of this video, but you can find them in Fairchild and Weibel's 1998 paper on LCD characterization. Once we know that the assumptions hold, we turn to the measurements that will allow you to compute the three model components: the primary matrix, the XYZ black level or flare value, and the RGB LUTs or lookup tables. The matrix comes from a measurement of XYZ of the primary channels, red, green, and blue, at full intensity, which for a typical display means a code value of 255. The flare vector comes from a measurement of the XYZ of black, meaning an input code value of 000. The lookup table comes from a measurement of XYZ of a neutral ramp, where ramp simply means a series of increasing or decreasing values, and neutral in this case means red equals green equals blue. So for example, here's a 52-step neutral ramp from black to white. Often people wonder about using ramps of each primary color, for example, from black to red and then from black to green to generate the LUTs. This will work, and ideally it would give you the same result. However, in practice, the additivity is not perfect. It may be off only by a few %, in which case the neutral ramp version puts the error way out at the saturated colors, while the primary ramp version would put more error around the neutral. Usually, we want to preserve the neutral, and we're more tolerant of errors around the edges. Now, the measurements for the verification must be an independent data set. They comprise a set of measured RGB vectors so that we know the corresponding XYZ. These actual measurements will be predicted with the model, and if the model predicts them accurately, then we know we have a good model. Good choices for verification will sample the entire RGB color space. This could be random, meaning choosing random RGB vectors and measuring them, or they can be organized, such as that set of 216 colors here. These represent a 6 by 6 by 6 grid in the three-dimensional RGB color space. How many verification measurements are enough? Well, how much time do you have? More is generally better, and I've used thousands before, but for a well-behaved display, something in the hundreds range, like this set of 216, is probably enough. So, once the spectroradiometer is set up and the RGB set is determined, measure everything. The verification samples are an independent set of data, even if you measure them in the same session as the model building samples. For efficiency, I typically measure them all at once. Next, build the model. Let's get into some details, starting with the primary matrix. The linear matrix M has 3 columns, populated with the XYZ measurements of each primary, with the black level subtracted. In fact, I should have mentioned that first. Pretty much the very first step in all of this is to find the XYZ of measured black and subtract that vector from each of the other measured XYZ vectors you'll use in the model building. Next is a tricky detail on getting from a measured ramp from a measured neutral ramp to a LUT. We have to convert neutral ramp XYZ values to linear RGB intensity. How? The solution is in the inversion of this same linear equation that is the core of our model. We compute the linear RGB intensity of each of the measured neutral ramp, meaning black subtracted XYZ values. These should all end up in the range of 0 to 1. We can then interpolate the red intensity to build the red LUT, the green to build the green LUT, and the blue to build the blue LUT. We usually interpolate for all integer inputs, corresponding to the typical 0 to 255 range of 8-bit digital inputs. Once these components are computed, the model can be implemented. It's possible to do all of this in a spreadsheet with Excel, but maybe I wouldn't recommend that unless you are uncomfortable programming. I would suggest MATLAB or Python, making 2 separate functions, a forward model and a reverse model, to go back and forth from RGB code values to predicted XYZ tri-stimulus values. Here's what I get with my Apple laptop display. The EOTF is actually very close to the standard sRGB, which means that Apple calibrated it properly before I got it. The black, white, and matrix values are all XYZ tri-stimulus values, where the luminance, Y, is in units of candelas per square meter. The verification of the model is the essential last step. As I mentioned, we have measured output XYZ values for a large set of RGB inputs. We push those same RGB inputs through our forward model to get predicted XYZ values. We could compare those directly to the measured XYZ, but it's better to convert both sets of XYZ to a uniform color space like CLAB and then compute a delta E between them. Here are statistics in delta E 2000 for my 216 verification patches. Overall, a very low level of error with a mean of 0.28. I'd say that Apple did a good job building this display, and likewise, I did a good job choosing a model form that fits it well. That's it for display characterization. I hope this was a useful video.